Hi, this is Albert van Dijk, and in this little video I wanted to talk about infrared remote sensing and in particularly mostly thermal infrared remote sensing. So we've talked about optical remote sensing before and thermal remote sensing uses very similar methods but looks in a longer wavelengths where you can actually see the emissions from objects on Earth directly essentially measure the temperature of those objects. That's one of the main applications of infrared measurement beyond the near and shortwave infrared. So I've got here a little diagram that shows you saw it before, it shows that in the short frequencies, the high frequency short wavelengths, most radiation coming from the Earth is not received by a satellite. And then we get into the visible and the near infrared regions where we do use extensively satellites to measure what goes on the surface. That gets extended into the shortwave infrared, which is particularly useful to measure things like water at the surface and the water content of vegetation, for instance. Then we get into the midwave infrared, which is less used in as it says here, a low transmittance window. In other words, a wavelength area where, again, the atmosphere absorbs a lot of the radiation being emitted from the surface. And then we end up in the more useful sort of long wave infrared and very long wave infrared thermal domains, again, where we can measure the temperature of objects. So just a quick sort of refresher reminder on what Planck's law tells us, which is that depending on the temperature of a body, the maximum emission frequency, in other words, the frequency or the wavelength where the radiation emitted is most intense, depends on its temperature. So we see here the example for the sun, which provides us with the light for passive optical remote sensing, and you see that because of its higher temperature, it emits in that spectrum particularly, and then you see that the Earth itself emits in the infrared domain strongest, but it also emits some radiation in the microwave domain, as we'll see later on. And that's true for ourselves and anything else with a temperature not too far off the Earth's average temperature. So that's what we're looking at. So how can you use that? Well, there's lots of ways you can use it, really. If you're interested in animal behavior, or particularly the way that animals regulate their temperature or regulate their life cycle, then thermal imaging can be really useful. So we see here exactly why a koala tree is hugging trees. A koala bear is hugging trees, excuse me. And you can see that in these white and yellow colors, you can see the high temperature of the koala, and you can see in the purple the much lower temperature of the tree. And so obviously there's an advantage to the koala to try and lower its core temperature a bit by hugging that tree. And you can see other animals have similar strategies. You can see that the elephant here uses its ears clearly to cool itself down. That's a very important mechanism. And also note, interestingly, how the emitted thermal radiation from the elephant reflects on the water before coming back to us. That's pretty interesting, isn't it? So it behaves very much like any other light. And here an example of a dog. You can see where it's losing most of its heat. You can see here a lizard, and you can confirm there's a temperature scale here in Fahrenheit, I suppose. You can confirm here that it really is cold-blooded, and the person holding it is still alive. And some other examples. So here's a little a video that you can also find online of one of the bats here waking up early compared to the other ones and starting to get active and heating up, and some depiction of the main places that penguins lose their heat in the Antarctic. So quite a few applications in ecology. It's quite interesting. There's also lots of applications to energy conservation, as you can imagine. You can see where's most heat lost from buildings, for instance. You can see which car has recently been driving. Police tend to use that a bit sometimes. You can see here a building that's losing a lot of heat compared to the other buildings. It could do with a bit more insulation, or maybe set their thermostat a bit lower. And also in terms of danger, the fire brigade usually does sometimes use thermal infrared cameras to see how hot the fire is, where the source of the fire is, and whether there's anything there that they should worry about. And here an example of electricity lines heating up to rather dangerous levels, and so good for building inspections and the like. So an environmental application that we have in Australia is called the Sentinel Hotspots website, or system that Geoscience Australia has been running for quite a more over the decade now, and that basically uses the same thermal measurement principle to measure where there are likely to be fires, because the surface is observed to emit thermal radiation at rates that suggest that it's hotter than a normal temperature. And so you see here an example. You can go to this website yourself. The links here on the side. You can go look there and see where recently fires have been detected. So just recalling Stefan Boltzmann's law. If you haven't seen it before, it basically gives you an equation to predict the irradiance, the amount of radiation emitted by a body at a temperature T in Kelvin, with a emissivity E, and what you see further in here is Stefan Boltzmann's constant, and the power 4, which is part of that equation. So what is the emissivity? Well, the emissivity is basically the ratio between the radiant flux from a real actual radiating body called a gray body, and that compared to a black body, which is an idealized body that has an emissivity of 1, essentially. In other words, it would be a perfect radiator, if you like. So the emissivity basically reflects the fact that real objects are not perfect emitters, and that emissivity and also that emissivity is a function of wavelength gives you important information on the type of material you're looking at, because that is an emissivity spectrum, if you like, much like a reflectance spectrum in the visible near infrared, and it's a material dependent feature. Now, there's different ways of using that. If you know the emissivity, for instance, of water, we know the emissivity pretty well, then we can actually calculate quite accurately the temperature. For instance, here you see the Atlantic Ocean, and you see currents there. And so to predict the current patterns and longer-term weather forecast, that can be really useful to tell us exactly where the current is currently going. Here you see the same. So this is a typical sort of image that shows you the principal component of El Nino, the pool of hot water here that moves east and west, and depending on that, there might be an El Nino or La Nina. At the bottom here you see cloud top temperatures, and again you can find this on the Bureau website, but you see there in white very low cloud top temperatures, and that's because the cloud is quite high up in the atmosphere and therefore cools down, and the higher up, the more likely there is to be a considerable rain coming out of that cloud. So it's a bit of a it's part of weather forecasting systems. They use this sort of information to predict the weather. You can also use the temperature of the land surface, and that's what you see here. So here you see that both geostationary satellites, in this case the GOES imager, as well as polar orbiting satellites such as MODIS and Landsat, can all measure land surface temperature and can do that at increasingly high resolution. And of course you can fly it with aircraft as well. What this picture tries to show essentially is that you can use that information to estimate the actual rate of water use by the vegetation, because as you know, when you evaporate water, you use energy to do that and you cool down the surface. So essentially, given with knowledge of the environmental conditions such as radiation and temperature and the like, or air temperature and the like, we can work out from the land surface temperature what the evaporation rate is. And so here we see that the cornfield in this case evaporates more water than the soil field. You can do similar things in irrigation settings and work out where are people irrigating, how much water are the crops using. And you can use it in sort of precision irrigation to map out which trees appear to be undergoing heat stress, for instance, and that's often an indication of a lack of water and maybe a blocked irrigation line or some such. So lots of applications of that in agriculture. Finally, there's also an application of thermal remote sensing, often airborne remote sensing for geological mapping. So if there's no vegetation, and that's a big if, but if there's no vegetation, you can use the emissivity spectrum of the land surface to determine basically what substrate you're likely to be looking at. So to illustrate that, this graph here shows the black body emission radiation of a body at a temperature that is known, 70 Fahrenheit in this case, and then it shows the measured emission spectrum here in purple. And if you divide the one on the other, you get the actual emissivity spectrum, which is what is shown here. And you see these sorts of features, and these features are mineral dependent, and therefore you can map out what the material at the surface is. So in this case, it's showing the emissivity spectrum of quartz, for instance. And here you see a number of values for different types of materials and rocks and such, but integrated over a broader range. So this is like a bulk emissivity, if you like. And so using that emissivity spectrum rather than the bulk emissivity, we can start to map out different substrate, different soil and rock types. And that's what you see here. You see a false color composite of a number of different bands being used, and you can start to see different geologies. And here's another example of that, where the geological mapping has been improved using the emission spectral information. And that was really what I wanted to talk about in terms of thermal imaging. And I guess there's a last little image there just to show that you're never safe, even if you think it's dark. The police might still be able to see what you're doing. So be warned.